Our sixth problem reads, charges of 1 microcoulomb, 2 microcoulombs, and 3 microcoulombs are placed at three corners of a rectangle 10 centimeters by 15 centimeters as shown in the figure above. What is the magnitude and direction of the electric field at the fourth corner? Let's look at the figure above. The charges are placed as shown here, the 1 microcoulomb in the upper left corner, the 2 microcoulomb charge down here, and the 3 microcoulomb charge over in this corner. The problem is to find the electric field up in this fourth corner, both its magnitude and its direction. Stop your VCR at this point and attempt to solve this problem. Here are our three positive charges arranged at the corners of the rectangle. I have also included the length of the diagonal, 18 centimeters. This figure was obtained by noting that the diagonal is the hypotenuse of a triangle of sides 10 centimeters and 15 centimeters and applying the Pythagorean theorem to that. The first thing we're going to do here is to determine the direction of the electric field due to each one of the charges. The direction of the field due to the 1 microcoulomb charge would be to the right. That direction is obtained by imagining placing a positive test charge at this point and imagining the direction in which that charge would be pushed. And a positive 1 microcoulomb charge over here would push it to the right. The field due to the 2 microcoulomb charge would be in this direction, and that due to the 3 microcoulomb charge would be straight up. We'll label these E1 due to the 1 microcoulomb charge, E2, and E3. Next, we're going to calculate the magnitude of each of these vectors by using the equation that the magnitude of E is equal to kq over r squared. For E1, the value of q is 1 microcoulombs and the value of r is 15 centimeters. Calculating the value for E1 and getting some room to do that, we would have that E1 is equal to 8.99 times 10 to the 9th Newton meters squared per Coulomb squared, multiplied by the charge 1 times 10 to the minus 6 coulombs. Divide that by 0.15 meters. If we write the centimeters as meters, that quantity squared. If you work this out, you should find that this is 4.00 to 3 significant figures times 10 to the 5th newtons per coulomb. And if you calculate in a similar way E2, you should find that that comes out to be 5.55 times 10 to the 5th newtons per coulomb, and E3 turns out to be 27.0 times 10 to the 5th newtons per coulomb. They are the magnitudes. Our next task is to add these three vectors together to find the resultant vector. We're going to do that by the method of components. Before we do that, we need to know this angle, let's call it theta, between E2 and the x-axis. The same angle exists down here, and down here we can find that angle by noting that it is the inverse tangent of 10 centimeters, the opposite side, over the adjacent 15 centimeters. And this turns out to have a value of 33.7 degrees. So that's our angle theta. You can move down here to a little cleaner figure where I have placed the electric fields. On this diagram, I have eliminated the factor 10 to the 5th newtons per coulomb for the time being to make it a little bit neater. The x components and y components of each of these vectors has been listed. for E1, the x component is just 4. E1 is purely along the x-axis. Its y component is 0. E2x is 5.55 times cosine of 33.7 degrees, which turns out to be 4.62. Its y component we can calculate to be 3.08. The x component of E3 is 0. It is purely along the y-axis, and its y component is just 27. If we add up the x components, we find the x component of our resultant vector to be 8.62 and the y component to be 30.1. We now have to find the magnitude and direction of this resultant vector. Let us draw another coordinate system, y-axis and x-axis, and we lay out our components along these axes. We have 30.1 along the y-axis and 8.62 along the x. The resultant vector will look something like that. It has a magnitude E, and it makes some direction with respect to the x-axis. Let's call it theta prime. The magnitude of E we can find from the Pythagorean theorem. It is simply the square root of 8.62 squared plus 30.1 squared, and that turns out to be 31.3, and I will put in the factor 10 to the 5th now newtons per Coulomb. So that's the magnitude of our resultant vector, the angle that it makes with the x-axis, the tangent minus 1 of that angle is the y component 30.1 over the x 8.62, and that angle then comes out to be 74.0 degrees. All right, that is our problem. We have solved for both the magnitude and the direction of our resultant electric field. Let us move on now to our next problem.